Hey guys, welcome back. So today we're going to start a very useful part of calculus in the real world, optimization problems. If you think about it, there are a lot of things we want to either maximize or minimize. We'd like to maximize our revenue and minimize our costs and all kinds of things. So this has a lot of real world application. Though, in order to keep the math simple, I'm going to start with not so much real world examples, just so you can understand how it's done. Okay, so I'm going to start with a very well-known problem. Okay, take a minute to read that. Okay, main idea. They're going to ask you to maximize or minimize something. Whatever it is they ask you to maximize or minimize, or make the greatest or the smallest or the least or the fattest or the smallest, anything that ends in an EST. Whatever the thing is they ask you to find the maximum or minimum of, you need to write an equation for that thing and then find its maximum, which means, as you know, find its derivative and set it equal to 0 and make sure the derivative changes from positive to negative. So without even reading this problem at all, just looking at these two words, I know I need to find an equation for area. Then I need to find the derivative of that area equation, set it equal to 0, and make sure that the derivative changes from positive to negative. That's my goal. That's it. You already know that. That's how you find a maximum. So the tricky thing is the word problem part of it. So let's get to it. We have a barn and a fence and a rectangle. Okay. So make sure you actually read the problem slowly. Make sure you actually understand what's happening. You have a barn. I'm going to represent the barn with just a straight line. Well, hardly even straight. Let me try again. Oh, a straight line. That's my barn. Coming off of the barn, though, is a rectangular garden. And it's a rectangle. Anytime they tell you the shape of something, you want to make sure you mark the sides. If it's a rectangle, use X and Y. If it's a square, use X times X. That tiny little piece of advice will go a long way to helping you get started on this problem, okay? So if they tell you the shape of something and it's a rectangle, X times Y. If it's a square, X times X. It makes a big difference. All right, so that little rectangle represents my fencing. But we're fencing this garden, and this is the garden here. So my fence, I definitely need a fence here, and I definitely need fencing here, and I definitely need fencing here. But do I need fencing where the barn is already closing it in? No. So we need 3 sides of fencing, okay? Now here's the thing with maximization problems or minimizing problems. What do we call this? Optimization, sorry. They often give you 2 equations that you have to work with. One of them is like the given information, and the other one is the one you have to optimize. In this case, they're telling us that there's 60 feet of fencing to work with. Well, what are they really telling us? What is actually 60? Well, looking at my picture, the thing that would be 60 would be X, another X, and a Y. Those things, the fencing, has to be a total of 60. So write an equation that represents the given information. 2x plus y has to equal 60. But that is not what they asked us to maximize. They asked us to maximize the area. So now I'm going to write an equation for area. Let me make a little space here. So the area of that rectangle would be x times y, because it's a rectangle. And remember, my goal is actually to find the derivative of the area equation. And remember to set it equal to 0 and check that it changes signs from positive to negative. Okay, I like to organize my work like this every single time. You're pretty much going to have one equation that represents the given information. Then there's going to be another equation you write that's the thing you're trying to optimize. But to help me remember that I still need to optimize it, I actually will write this step right at the beginning, just like I did, because I'm now going to have to write this area equation, and I'm still going to need to remember to get the derivative in order to maximize it, okay? So I typically make a pattern or a habit of myself of chunking this type of problem into 3 sections, okay? The given information, the equation I need to maximize, and then when I actually do maximize it by getting the derivative. Okay? So now what I need to do is let's focus on this equation. Right now we have too many variables. We need to rewrite it in terms of one variable. So I have x and y, and I want all x's or all y's. So that's where the first equation comes in. You basically use this equation, isolate either one of the variables, whichever one's easier, and then plug that into the equation you're trying to optimize to get rid of one of the variables. Okay, so I need to clean this up again. Give me a minute. Okay, so I think in this equation it'd be easiest to get the y by itself. So I get y equals, subtract the 2x, and it's 60 minus 2x. It doesn't matter which variable you isolate. It just tells you you're going to get different order of answers. If you solve for x, you're going to get a different answer in a different order, but we're both going to get x and y. It's just which one do we get first, okay? All right, take what y equals and plug it in for the y in this equation. So now I have a equals x times. Replace the y with what it equals. And this is the area equation that I now need to optimize by doing the derivative. Now we can leave it in the format that it's in right now and do a product rule, or I think it would be easier to distribute and then do the derivative. So I'm going to clean it up. And now I have to still remember, again, that's why I write this step right here. Now I still need to find this derivative. We found a formula for the area, but we didn't maximize it yet. So the process of maximizing it means find its derivative. 60 minus 4x. Set it equal to 0 and solve. Move the 4x over. Divide by 4. And what do you get? 15? Now, you can't just write with word problems. You can't just say x equals 15. You're the one who made up the x to begin with. I put that x over there. So always make sure you reread the question, because I could ask many questions. I could ask for the length of the, I forgot what this was, garden. I could ask for the width of the garden. I could ask for the perimeter. I could ask for the area. I can ask a bunch of things. So what they want to know is, read the question again. What is the maximum area we can enclose? Well, this is the dimension that will give that maximum area, but now I got to find the area. So I have x. To find the area, I would also need y. We're basically looking here. Well, can I get y? Where's y? Where's y? Oh, there's y. So to get y, we're going to plug into that equation. 60 minus 2 times 15. So 60 minus 30, that would be 30. That means the dimensions are 30 by 15, and nobody cares which order you write that in. That would be the dimensions. Did I answer the question yet, though? Nope, because they said, what is the maximum area? So I actually have to multiply those. The area we'd be looking for is 30 times 15, 450 square feet since it's area. Okay, I want you to look back through that problem, okay? That's the main idea. You're going to have basically two equations most of the time. The given information and the thing you need to optimize. And then don't forget, in order to optimize, once you get that equation, you still have to actually get the derivative. Now, notice I didn't check and show that the derivative changed from positive to negative. That's because in these types of problems, often they could trick you. They could make it a minimum. So I really should check. That x actually gives a minimum. And I could do that in two ways. I could do a first derivative sign chart, or I could find the second derivative and plug it into that and use a second derivative test. Now, the reason I'm not really going to bother checking that one is, if you think about it, this problem is going to be a minimum anyway. I'm sorry, it's a maximum. This problem is only going to have a maximum. It's not going to have a minimum, because what would the minimum amount of fencing be that you would ever need? What's the minimum area you would ever need? 0. So the people who write the question, they know that this one's going to give a maximum. But you can use your common sense to see that you don't really need to check that one. But it wouldn't take long to do a first derivative sign chart. Okay, next one. Okay, I want you to read it slowly. This is a question that you really could do with guessing and checking. And you've been doing this question probably since the 3rd grade. But we're going to do it, well, with calculus. So we need 2 numbers. I guess I'll call one of them X and one of them Y. Okay? Their sum is 60. 2 numbers whose sum is 60. So X plus Y has to equal 60. Got it. Whose product is as large as possible. Product is a maximum. So I need to write an equation for the product, and then I need to maximize it. It's kind of weird though, because product would be X times Y, but I need to give it a name. I need to have an equation here. So I'm just going to call it the product is XY. And it's the product that I'm trying to maximize. Okay? So those are my 3 equations. Now, I like to always give this thing that I'm trying to maximize, always give it a title. On the AP exam, that allows you to get credit for when you are able to justify it, and you can refer to it and say, oh, and I'm going to get its derivative, and I'm going to set it equal to 0, and make sure it changes from positive to negative. So it's very important to give it a title. Seems silly, but it's very important, okay? I don't know if you guys can hear, they're cutting along, but they're sorry about the noise. All right, so the given information was 2 numbers have a sum of 60. The thing they want us to maximize was the product, okay? And then this is how you're going to maximize it. It's sometimes confusing to people because you've got 2 equations. One's the sum and one's a product. Just make sure you pay attention to the one you need to get the derivative of, and that's the one you're trying to maximize or minimize. All right, so once you get this set up like this, once I show you how to set it up, from here it's easy. This is the one I'm going to do the work to, because that's the one I need to get the maximum of. So do the same thing we did on the last problem. Get rid of one of the 2 variables. So I'm going to solve for y again. I don't know why, just because. Take what y equals and plug it in right there. Distribute because I can, and it makes life easier. And that's my equation for product. Now, maximum product derivative. So find its derivative. Always write that step. Okay, find its derivative, give it a title. 60 minus 2x, set it equal to 0. 60 equals 2x, so x is 30. Again, you made up the variable x, so don't just say that. Find 2 numbers. That's what the directions said. So x is 30, and that means y is also 30. Okay? And you can check it with some common sense. All right, this one. Next one. Okay. What is the smallest perimeter? I keep doing that, sorry. What is the smallest perimeter? So I'm going to be looking for perimeter of a rectangle. Well, I sometimes kind of need to draw it, but you know, it's up to you. It's a rectangle, x and y. Okay. Smallest perimeter. So I'm going to write an equation for perimeter. I'm going to have to find the minimum by getting the derivative and make sure it changes from negative to positive. Okay? Well, the perimeter of a rectangle would be 2x plus 2y. So there you go. Feels like I'm on the right track, but too many variables. So where's my other variable? Oh, the area is 36. Area of a rectangle, x times y equals 36. Now, I know from experience that I make that seem like it's super easy, and then you get home and it's not so easy. But notice my pattern here. Whatever it is I'm trying to find the smallest or biggest thing of, I always write that equation here. I always prepare for my derivative over there. And then I need some sort of given information so that I can get rid of the fact that I have 2 variables. Over and over and over again. And if it's geometry, draw a picture. Okay. From here, this is easy to solve. I would like to see you do it. Hit pause and give it a shot. Okay, I did some of it. I solved for y. I took what y equaled and I plugged that in over here. But I know some of you get stuck in your algebra, so let me make sure you know what to do with that. Just multiply straight across, and that's going to be 72 over x. And I can rewrite it like this in order to do the derivative more easily. Okay? Now I find my derivative. You go ahead and do that. Hit pause again. Okay, so there's my derivative. This was negative 72 x to the negative 2, so I rewrote it with a positive x squared on the bottom. Now, normally I'd say get a common denominator, and you can, that's fine. But since I don't really need to worry about the denominator in real world problems, usually, because, if I have x of 0 and x represents the length of a square, if the length of the square is 0, you don't have a square. So because of that, you can usually just say equals 0 and not worry about the undefined. Solve that, move the 72 to the other side, multiply both sides by x squared, or cross multiply, however you want to think of it. I got to rewrite that. I'm at this spot right here right now. Ignore this. And cross multiply or multiply both sides by x squared, and you get 2x squared equals 72. Divide by 2, and x squared is 36. Square root, we get x equals plus or minus 6, but you can't have a negative length of a square or a rectangle. So there you go, x is 6. And that's going to mean if x is 6 and x times y is 36, then y is also 6. Now, what did they say? What's the smallest perimeter? I didn't even answer the question. So always reread the question. What is the smallest perimeter? Well, that means I need to actually plug it in here to get the perimeter, or use my common sense. If this is 6 and this is 6, the perimeter will be 6 times 4, 24. And what are my units? This is perimeter, and area is 36 square inches, so this is 24 inches. Okay, pretty much we're going to do the same type of thing over and over again. See if you can set this one up. Hit pause. By saying, when I say I want you to set it up, I want to see those 3 equations, okay? Those 3 sections. So we need 2 positive numbers. Don't worry about that. That's up to the writer of the question to figure that out. I need 2 numbers whose sum is 45. Okay, I got that. X plus y equals 45. Check. Done. Such that the product of the first and the square of the second is a maximum. Okay. The first, I don't know which one's first or second. I'll just call the first one x. The product of the first and the square of the second is a maximum. I got to give this thing a name. I'm going to call it P for product. Okay? This is the thing we want to maximize. So I'm also going to note, I'm going to eventually look for this. Okay? So the product of the first and the square of the second. And I had to give it a name. Hopefully you were able to set that up on your own. Now, solving it's going to be pretty much like all the rest. So hit pause if you want to, or you can watch me solve it, whatever you prefer. I'm going to this time isolate x because I don't want to have to square. So if I get x by itself, I think the problem will be a little easier. Plug that in. Distribute. And now I need to do the derivative. And always give everything a title, P prime. When we start getting into more realistic word problems, that's going to be huge. And it is on the AP exam always. And you get points just for knowing what your goal is and being able to put it into symbols or words. Okay? Now I'm going to find that derivative. 90 y minus 3y squared. Set it equal to 0 and do your thing. Okay, factor, I can factor out a 3 and a y. And I'll be left with 30 minus y. Set each factor equal to 0. We get 0 and 30. So there's 2 possible answers. Oh, okay. Well, let's see. If there's 2 possible answers, one of them could be a max and one of them could be a min. So now you're stuck. You really have to check or plug them both in and see which one actually gives you that maximum product you're looking for. When you plug them in, you're going to have common sense approach. So when y is 0, I'm going to do my first derivative sign chart, I guess. Okay, plugging in right here. In between 0 and 30, I could plug in a 1, and that would give me a positive positive. After the 30, I could plug in a 40, and I'd get a positive times a negative. I think that already makes it pretty clear that the 30 is the maximum we're looking for. If you think about it, they said we couldn't have anything negative, but if we had plugged in a negative number, this would have been a negative, and that kind of tells you it's a min. But also, if my graph is increasing after it, then, and this is an endpoint, then it's sort of still a min, okay? So our maximum will be the 30. So let's reread the question. Find two positive numbers whose sum is 45. Yeah, we just need to find both numbers. So y is 30, and when y is 30, x will be 45 minus 30. So x is 15. So we want the answer of 15 and 30. Now, to verify it, just for your common sense, plug this solution into this equation, and then plug the other solution in, the one that we canceled, the one that we said, nope, that's going to be a min. If you use 0, the other number would be 45. So 0 and 45 was a possible solution, but I want you to verify that that's actually a minimum by plugging it in here, and you'll see, okay? I think this is getting a little redundant, but what the heck, I'll do one more. Okay, so smallest perimeter. So we're going to be, and it's a rectangle again. I'm going to draw it up here. It's a rectangle. I call that x and y. Smallest perimeter. So the perimeter is 2x plus 2y. To make it the smallest, I need its derivative, and it needs to go from negative to positive. And we need the given information. Oh, the area is 25. X times y is 25. Okay? Go ahead and solve it if you want to, or you can watch me. Either way, hit pause if you want to do it on your own. Get y by itself. If it was me listening at this point, I'd be doing fast forward. Like, I already got it. I got it the last time. I don't need to see another one. But, I can't help it. So you don't have to watch this last one. Let me see. Replace the y with 25 over x. It's just like the other one we did. So we get 2x plus 50x to the negative 1. Do the derivative. 2 minus 50x to the negative 2. Set it equal to 0. Move the 50 over. Cross multiply. I'm running out of room again, just like I did the last time. Okay, cross multiply. 2. Just rewrote it. Cross multiply 2x squared equals 50. Divide by 2 and x squared is 25. Square root x is 5 or negative 5, but you can't have a negative length of a rectangle. Okay, let's make sure we check what they asked. And by the way, you're probably seeing a pretty common pattern for the answers to these things. Okay, what is the smallest perimeter? So I've got to plug it in. Well, if x times y was 25, if x is 5, y has to also be 5. And if these are both 5, then the perimeter is 20. Okay? Inches. All right, good luck, guys. I really did try to just keep it to the easiest type of problems for today. It'll get a little harder each day, a little bit at a time. Here is your assignment, and hopefully I kept it decent for you today. Good luck, everybody. Hope you're doing well.